Hello everyone, myself Kare from VPKBIET Baramati. Today's topic of discussion is NP hard and NP complete problems. So before starting the discussion of NP hard and NP complete problem, we should understand some basic concepts. To relate all these, here I have written exponential time problems, that is 0-1 knapsack problem, traveling salesperson problem, sum of subset problem, graph coloring, and so on. All these are the exponential time problems. To relate these exponential time problems to each other, we should have a base problem. We need some base problem that is similar to it. So we will take a base problem as a satisfiability problem. Now what is a satisfiability problem? Satisfiability problem is basically a CNF formula. It is a propositional calculus formula using Boolean variables x1, x2, x3. So for example, consider this is a satisfiability problem having the CNF formula as x1 or x2 bar or x3 and x1 or x1 bar or x2 or x3 bar. So this is basically a conjunction of disjunctions. Now what is the solution to this problem, to this satisfiability problem? So for what values of x1, x2 and x3 the given formula is true, that is the solution for this satisfiability problem. So here I have listed out possible combinations of three variables x1, x2 and x3. As there are three variables, there will be 2 raised to 3 possible combinations, possible solutions. If there are n number of variables, then there will be 2 raised to n possible solutions. So it means that this satisfiability problem also have exponential time complexity. So it also belongs to the exponential time of the algorithms. Now we will see the solution to this satisfiability problem in the form of state space tree. So here is the state space tree drawn with possible values of x1, x2 and x3, and the solution is represented in terms of state space tree. From this state space tree you can observe that there could be 8 possible solutions like this 1 1 1 1 1 0 1 0 1 in this way. So this is the state space tree solution to this satisfiability problem. Now here I will take another problem, that is a 0-1 knapsack problem from this group of problems, that is exponential time problems. So consider this is one instance of 0-1 knapsack problem having 3 bits like 5, 4 and 3, and profits are 10, 8 and 12, and the capacity of knapsack is 8 given over here. So what is a knapsack problem? We have to fill the knapsack with the given capacity and with the given weights such that profit should be maximized. So what is the solution for this problem? The solution will be in this form, that is 3 tuple solution over here, as there are 3 weights. So I can list out the solution in this format as well, that is x1, x2, x3 having different values 0, 1, 0, 1 like that. So x1 will be either 0 or 1, x2 will be either 0 or 1, x3 will be either 0 or 1. So how many possible combinations are there? Again here there are 2 raised to 3 possible combinations. If there are n number of weights, then there will be 2 raised to n number of possible combinations, and the solution also can be represented in terms of state space tree. So this solution is similar to the satisfiability problem. It means that satisfiability problem can be converted into the 0-1 knapsack problem, and 0-1 knapsack problem can also be converted into the satisfiability problem. In this way we showed that the relationship between the exponential time algorithms to the satisfiability problem. So now we will add the satisfiability problem into the exponential in the list of exponential time algorithms. So I will add over here this satisfiability problem as a part of exponential time algorithm having the time complexity 2 raised to n. Now here we are ready to coin the term NP hard. So before understanding this term NP hard, just call these all problems, these all exponential time problems, 0, 1 abstract, traveling salesperson, sum of subset and so on, as the hard problems. Instead of calling it as a NP hard, I will call it as a hard problem. As satisfiability problem is a base problem, we call it as a NP hard. So now I am calling to the satisfiability problem as a NP hard, and for other problems which belongs to the category of exponential time, I will call it as a only hard problems. Now to show the relationship between the satisfiability problem and other exponential time algorithms, the procedure is a reduction. Now we will understand what is a reduction. So reduction is a procedure to show the relationship between the satisfiability problem and other exponential type of problems. So for example, consider this is a satisfiability problem. If I try to reduce it into the 0, 1 knapsack problem, for that purpose I will take the instance I1 of the satisfiability problem and instance I2 of the 0, 1 knapsack problem. Then if 0, 1 knapsack problem can be solved in polynomial time, then same algorithm can be used to solve the satisfiability problem, or vice versa. If the satisfiability problem can be solved in polynomial time, then the same algorithm can be used to solve the 0, 1 knapsack problem. So conversion, for this conversion it will also takes the polynomial time for converting one problem into the another problem. Now we will try to understand the NP hard concept. If I convert the satisfiability problem into the another problem, say L is another problem in the category of exponential time algorithms, then as the satisfiability is a NP hard problem, as why satisfiability is a NP hard problem? Because it is having the non-deterministic polynomial time algorithm at present. Means satisfiability is a well-known problem which is having the non-deterministic polynomial time algorithm. If I convert this satisfiability problem into the another problem L in this given list, then that problem also becomes the NP hard. And if I write the non-deterministic polynomial algorithm for that problem L, then it enters into the NP complete category. So this is very important what I am saying. Satisfiability problem is a NP hard problem. If I convert satisfiability problem into any other problem, say L in the list of exponential time problems, then that problems becomes the NP hard. Now to become that L problem as a NP complete problem, what I have to do? I have to find out whether there is an algorithm for this L problem which is non-deterministic polynomial time algorithm. Then that problem becomes the NP complete problem. So here we will see with the help of a very well-known diagram of NP hard and NP complete problem. This circle indicates these are the NP hard problems because satisfiability is a NP hard problem, and all these problems can be converted into the satisfiability problem, or satisfiability can be converted into these all problems. So these all problems are also the NP hard. So satisfiability problem is NP hard, 01 knapsack problem is NP hard, craft coloring is NP hard, sum of subset is also NP hard. Along with that, satisfiability is having a non-deterministic polynomial time algorithm. So it is also in the category of NP complete. So here in the shaded area, I have shown the satisfiability as a NP complete problem, because basically it is a NP hard, but it is having non-deterministic polynomial time algorithm. That is why it also is in the category of NP complete. So those NP hard, if any problem which is NP hard is having non-deterministic polynomial time algorithm, then that problem becomes a NP complete. What I am saying, once again I repeat this statement: if any problem which is NP hard is having non-deterministic polynomial time algorithm, then that problem becomes NP complete. Satisfiability is a non-complete problem. So I have shown over here the relationship between NP hard, NP complete, and NP and P problems. So these are the non-deterministic polynomial time algorithm, and these are the deterministic polynomial time algorithms. Now let's have more discussion on it. Now there is a very famous theorem, that is Cook's theorem. What Cook says, that we will try to understand over here. That is, if satisfiability lies in P, what Cook says, if satisfiability lies in P, if and only if P is equal to NP, it means that if satisfiability is having a polynomial time deterministic algorithm, then all your non-deterministic polynomial algorithms will be the deterministic polynomial time algorithms. So if satisfiability lies in P, then P is equal to NP. So that is the statement of Cook. That is the theorem of Cook. Though it is not proved, that is, satisfiability lies in P, or satisfiability is having the polynomial time deterministic algorithm, but the theorem says that if it is the case, then P becomes NP. So this is about the NP hard and NP complete problems. I hope you all have understood it.